Well, good morning, grade 12s. Um, so here we are in our closet at home, and I have set up a little experiment that we'd normally do together in class. Okay, and what you're seeing here is a laser beam, and you're seeing a ruler that I taped to the wall. Okay, and yeah, so anyway, this is a little double slit experiment, and I think I told you yesterday when we talked about Young's double slit experiment. He used a single and a double slit. He used the single slit to make sure that the waves arrive at the double slit in phase. Okay, we don't need to do that with a laser, because the beautiful thing about a laser beam. So here, you can see there's a laser here. I'll put the path in there. You can sort of see that laser, and it's hitting this like apparatus right here. Okay, actually, before you see this, before we do the experiment, you can see how the slits are arranged. Okay, so you can see that there's a double slit on the top left of this little glass filter here. Okay, so at the top left you'll see, like right there, you'll see a double slit, and then they get closer together, so D is getting smaller, like the variable D. Okay, and then even closer together there, and I've picked the one that's second from the bottom. The one at the very bottom, for some strange reason, is a single slit, which we don't want. You can see the laser beam hitting one of the double slits though. Okay, so it's hitting that one down there. Okay, and then shining over there onto the wall. Okay, now I've got a tape measure there to measure L, the distance from the wall to my double slit. Okay, it's not the distance to the laser. It's the distance to the double slit. That's where my two sources are, right? Okay, and so if you come here and look at this, we can clearly see an interference pattern here. Okay, not just two bands. There's two holes, there's two slits, right, that the laser light is passing through. We actually see many, many bright and dark spots there. Okay? Radiating outward. When I turn out the lights, you'll see it even better. So that's the experiment. And the beautiful thing, as I was saying, the beautiful thing about the laser beam is with the laser, you don't need to have, okay, I'm going to turn out the lights. With a laser, you don't need to use the single slit like Thomas Young did, because lasers produce coherent light, which means that the waves all come out of the laser in phase. Now my phone's probably going to have a problem with focus. But anyway, I've got a little like spray bottle of water. And if you were here, of course, I'd probably want to spray you with it. But you know what? You're not here. So I'll just have to spray the laser. So here you can see, okay, the laser light coming out. There's some reflection there. Okay, it hits the double slit. But the cool thing is, over here on the wall, look at all those bright and dark spots. Okay, it's very bright in the middle. You see lots of bright and dark spots. That's double slit diffraction, right? Like what we're seeing here is the interference pattern. Okay, and here I want to show you, like the light is coming from that beam over there, and if I spray here, you can see really, it's not too great with the water drops. You can see the lines, the nodes and antinodes. Right, see that? Okay, so that is the nodes and antinodes there. Okay, all right. So I'm going to turn on the light again. Okay, so I'm going to turn on the light, and here I've made measurements. So what I've done is I've set L, okay, like here, it's 2 meters exactly. I made it a little bit more than 2 meters just because the ruler is slightly off the wall. So I tried to make it exactly 2 meters. I made it that way on purpose. Wow. And then to get delta X, okay, what we do is we're going to look at this pattern of bars here, okay? And this is why the ruler is here, is so I can measure the distance between the nodes. So here you can see, you can see my finger, here at around 5 point, like the, it's actually at the 45 centimeter mark, but anyway, at around 5.5 is the edge of one of the antinodes, okay? And then if you move over here to around 6.4 or so, okay, you'll see the edge of the next one. Now, just for measurement error, I want to not measure just one delta X. I want to measure several, okay, and take an average. And that will reduce my measurement error, okay? So, you know, let's say I start over here at the one that's close to the 6. Okay, that one there is probably pretty good. Okay, so I'll measure the one that's pretty close to the 6 there. Okay, my phone is blocking some of the light, so it's blocking some of these notes and antinodes, but that's okay. All right, so I get 6.4, right? And the phone does not expose the bright lights well, but I'm going to move over 1 delta X, 2 delta X, 3 delta X, 4 delta X brings me to 9.5. Okay, so 6.4, 1, 2, and 4 delta X's brings me to 9.5. Okay, so 6.4 to 9.5 for 4 delta X's. Okay, so I'm going to stop this here so you can see the apparatus. This is the laser apparatus. And what we're going to do is we know the wavelength of the laser. It says on there that it's 636 nanometers. So what we're going to do is we're going to take that and we're going to find out how close those slits really were. Okay, so we're going to determine D. Okay, all right, so I'm going to stop here and then we're going to go and just do the quick calculation in the notes.